Gowthami, and today let's talk about like diffusion models a little bit. Okay, so we have all seen these great sort of generations coming out of like great models coming out of these labs, which are capable of doing like a lot of tasks, right? Here I kind of show like a snapshot from Google's latest Veo model. I took up a screen grab from this Float TV. And as you can see, they're able to like make all these animals, make the hearts and so on. Similarly, we also we can say image generation is a more or less pretty much solved problem in terms of text image, and we are able to like achieve like different types of variations, like a lot of control and so on. And this is again like a string grab from galleries from like Adobe Firefly. Okay. Right. So before we get started, a little bit of a disclaimer. This tutorial, I kind of try to target it for beginners. So the concepts could be like oversimplified at times. And so if you already know like a lot about diffusion models, you might not be learning a lot today. And lastly, another disclaimer, there were going to be a lot of cats. I wanted to maintain a theme, but so I decided like everybody loves cats. So yeah. So as you can see. And another thing is all the illustrations more or less are generated using Adobe Firefly with the prompts you can buy Google Gemini. Cool. Okay, on high levels, these are the 4 topics I'm planning to, I'm going to talk about diffusion models. I try to sort of segregate them into different subgroups, so that we can have a break and have it, if you have any questions, I try to answer them in between these sections. Okay, in the first section, I'll go over a little bit about what are generative models, and in the second section, predominantly, which is going to be the largest section of this talk, going to talk about diffusion models, especially DDPM. And in the third section, we are going to talk about a little bit of general formulations, like DDIM, what is introduced in DDIM, or most recently, there is something called diffusion flow blog post that came out of Google DeepMind, where they try to find unified formulation for diffusion models and flow-based models and so on. And lastly, I'll touch a little bit about guidance, how do you control the generations in diffusion models and so on. Okay, cool. Yeah, let's get started. So generative models, in this talk, I'm going to mostly talk about image generative models. So we all know what they are. We kind of give a prompt and then we kind of end up with a generation, either realistic looking or imaginative, and so on. So let's think of what is a generative model for a second. And let's say we are kind of think of all the images are coming out of a process, a probability distribution, where when you sample, you are getting one image at a time. So you can think of it that way. There is some generative process, a probability distribution P, which we don't know what it is. And the whole field of generative modeling is about how can we train or find an approximation for this probability distribution, where all these images might be being generated from. So during training time, let's say we have this internet scale data sets from Lion, and we can think of them as they're all coming from some generated distribution. And during inference, we want to come up with an approximate probability distribution, which we can sample from, given some latent variable. How do you sample from a distribution? You need to start from something, right? It can be latent variable, or your latent variable could just be a text font, or and so on. Okay, traditionally, in most of the older generative models, usually this latent variable tends to be some noise which is sampled from a known distribution like Gaussian distribution. So usually Z means a noise variable. Okay, and the next thing is how do you guide or control in the generative models? If you think about text to image case, sorry, let's just take one of the early diffusion models, with no conditioning. All you can do is you can sample a noise and you can get somewhat realistic looking image out of it. So in the if you take that model and let's say you want to generate a dog, But you have to keep sampling. Like when there is no guidance, like you have to keep sampling until you accidentally pounced upon an image that creates a dog, right? Like so, and we shouldn't be doing that. Like there should be an easier way to sample what exactly we want, and it shouldn't be conditioned only on like random noise. It should also be conditioned on some sort of a signal which humans can provide, right? Like so, that's what usually what conditioning or control is. Like it's represented by this variable C. And here I'm giving some examples of what possible conditions could be. Like it could just be like a really long prompt, like where we are kind of giving out these details of like what the object should look like, or the camera focus and what the background should be, and so on. Or we can just give the depth map of the image. Like, okay, we have this depth map, and I want to create an image like which has a depth map similar to it. Or we can just give the edges, or we can give like a part of the image like masked out and we want to fill it. Or we can just give like another image with like a completely different modality. Like here a picture is a cartoon, right? Like, and we want to turn it into like a real image. So what I'm trying to say is like this conditioning, like usually you hear conditioning as like usually text or something like that. It doesn't have to be. It can be another image. It can be video. It can be anything. Like conditioning can be anything. And in math terms, like you kind of say like we want to learn this probability distribution where we can produce X, which is like an image that is coming out of the image distribution, and give it, which is conditioned on some random noise along with some conditioning. Okay, so these are some of the generative models like which we have seen in like I would say past 10 years, where we have successfully created the images more than a mist, and VAs and GANs like sort of came out around I would say like almost 6-7 years back, where the generations are like they were able to like do reasonably good generations on like ImageNet scale, and most recently we have diffusion models like I think like they came out around 2020 time. I mean, diffusion, the theory of diffusion models have been around for a while, but diffusion models like started actually working like around 2021 sort of. Okay, and I mean, in fact, like autoregressive models are also type of a generative models. But today I will mostly be talking a little bit about VAs because they have like very strong connections with diffusion models, and then we'll be talking about the diffusion models. Okay, so just to give you like a super basic idea, when I say latent space, like we have some sort of a distribution, like, I mean, because I cannot represent in any space more than 3 dimensions on a paper, so I have to massively approximate. So we have like this 2D latent space, and then we want to travel from this 2D latent space to like realistic looking image space. Like, so we have this image space, which is like a really high dimensional and so on. And we want to learn a neural network, taking this conditioning and some point which travels from this some random point in this latent space to a realistic looking image in this image space. Traditional generative models like GANs or VAs sort of like do it in one step. Like you just sample and then you just immediately like you do one forward pass and like you end up with like an image, right? However, diffusion models kind of do this in multiple stages. Like you take one step and then go another step, you take another step and go on. Like and one important thing to notice is like this is not always the shortest path. Like you are kind of like exploring in the space and eventually you will get to the image space. And so our main objective when you are doing the generative modeling, like to train a diffusion model is usually like how to train this neural network. And that's what all this research is about. Like how do you train a neural network that can take like a latent noise and then we end up with like a realistic looking image. Cool. Like I mentioned before, it's usually, okay, so first of all, like when you take an image, like even a small image, like 32 by 32 pixels, I mean, the dimensionality of it is really high, right? Like it's 32 into 32 into 3, like approximately like 1,000 dimension space. So, and it's very hard to show the, I mean, it's not possible to visualize like more than 3 dimension space. So, and diffusion models, since it is time dependent, it would be nice to like see how the points are moving over time. So that's why I'm going to take like a really simple case. Here we have a 2D space where each point is uh, is what I'm interested in. It's a sample. It's a training sample for me. And then this is what our training data is. And then we have the noise distribution, which is a 2D Gaussian. And we will see like at different stages, like how coins are moving across time in this two-dimensional space. That TLDR, I'm going to use this as like a running example throughout this talk. Okay, so the next question that might come up is why are diffusion models like so famous? So the first thing, state of the art sample quality, as you can see, like this is the main reason they generate images with the unprecedented realism and detail, setting like a new standard for quality. And as you can see, like this is the technology behind like Midjourney and all these very successful image generative companies. And the second thing is like the training is like really stable. Like I mean, if you have trained GANs, like you might have seen, the model randomly collapses. Like it sometimes you don't even have to do anything. Just change the seed, and like the training is successful. Like so, it's extremely unstable training, like for GANs. So, however, in diffusion models, you don't technically see it. The only caveat I would say, like in training diffusion models, is you need to train it for really long. And as long as you are able to give like a lot of training iterations, the model will converge. Like no matter, as long as like there is a reasonable sample quality, it will converge. And the third thing is it's grounded in math. So the main reason is the model being like diffusion model success not exactly is because it's grounded in math. But why I mentioned this point is like because it's grounded in math, like we are able to come up with like various different variations in terms of loss function. I mean, it's more of a guided sort of a search when you're trying to come up with like what sort of noise should be added along different time steps, or how the loss function should be weighted, and so on. Like it can be a little bit guided, like search rather than like a random search, like how most of the empirical deep learning is these days. And the next point, like the flexibility in modeling, kind of comes back to the same thing. Like there are like a lot of different moving parts in modeling diffusion, and we can kind of play around with them and like make the models even better. Like even now, people are discovering like different ways to make diffusion models better. Okay, and the next important point is like the inference time scaling is built into it. Like, if you have been following the trends in deep learning, like inference time scaling is like a really big thing this year. What does it means is like you can give like increasing number of flops to kind of come up with an answer during inference time. So if you know a little bit about diffusion models, you already know like diffusion models, like we can do like a various number of steps. Like you don't end up with like the final image in one shot. Like you kind of do a lot of shots. A lot of steps to get to the final image. So this is already built into the way diffusion models are designed. And lastly, like it's just a great timing. Like diffusion formulations came out in the scaling era, where we have like large data sets and like a lot of compute and a lot of interest in deep learning. Like a lot of money was pumped into it, and many smart people were like working on it. So it just made these models like really, really good because a lot of resources went into it, like either compute-wise, data-wise, or even like brilliant minds-wise. Okay, so yeah, let's just begin. In this section, I tried to keep math as little as possible since it's a summer school, and let's try to build intuitions rather than like focusing on the math. So there will be big equations, but please try to like not focus on slides too much. Just try to pay attention to me because most of the huge terms usually boils down to some constant. Okay, like so don't be scared. Feel free to stop me and ask a question if something is not clear. Let me keep the questions tab open. Okay, cool. So I want to give like a couple of basics about, in general, like Gaussian distributions. Like it has nothing to do with diffusion models yet. So first of all, like diffusion models, like a lot of the math is kind of based on Gaussian distributions. Like how do you add two Gaussian distributions? And so on. It's a lot of Gaussian math. Like there will be a lot of terms. However, it boils down to very, very simple statistics given like right assumptions. Okay, let's just try to remember a couple of these things because we'll be utilizing them later. Okay, so first thing is when you have like two Gaussian distributions with the same variance, the Cohere divergence, which is usually like used to measure like how far these two distributions are apart from each other. So the Cohere divergence between these two distributions boils down to some L2 distance between the mean of these two Gaussian distributions scaled by some variance term. Like since sigma square usually like it's predefined, we already defined it. So it's again this is a constant term, and then the main term to focus is it's just L2 distance between the mean of these two distributions. Again, like this is under the assumption that they both are isotropic Gaussian. That means like different axes between, I mean, if it's a multivariate Gaussian, that means like it has a lot of dimensions, right? Like, so all these dimensions are not correlated with each other. And the second important assumption here is like they both have the same variance. Okay, and the second important map fundamental you need to know is how do you sample from a Gaussian distribution with the mean mu and variance sigma square. Again, this is very simple. You can approximate it as you have some defined like let's say your x is coming from this Gaussian distribution with mean mu and variance sigma square. Then you can define another random sample epsilon, where you are sampling it from a normal distribution, like with mean 0 and variance 1. And then all you can do is you just scale this. Oh, sorry. This should be epsilon. Yeah. Okay. So all you have to do is, I mean, again, like this should be epsilon. All you have to do is like just scale it by the standard deviation and add the mean. Like it's just scale and shift operation. Like that's all. Okay. All right, now let's begin. Like first, let's kind of try to understand like variation autoencoder. It kind of a lot of intuitions sort of transfer like to diffusion model, like if you kind of get this a little bit. Okay, so I have already mentioned before that like most of the generative modeling, like paradigm, I mean, especially like the probabilistic modeling, we kind of assume there is a latent variable which is coming from the distribution we can sample from, and then we want to learn a function like a probability distribution, which like theta usually means like P of theta usually means like a neural network, where you can kind of, once you pass this latent variable to this function, the output of it will usually be like an image or whatever data you are trying to model. So that's what, like we want to learn a function which can take an input from a known noise distribution and then can produce like a realistic looking image. Okay, so and then if we assume like the again like here I'm just showing like this one is like the log likelihood of a given sample under this distribution. And again, like I said, like we want to sample Z from Q, like which is a known distribution, like a Gaussian or something like that. And then if we compute like the and if we assume like this P theta function, like this distribution we are trying to model, let's assume its mean is predicted by a neural network, and it will have like a standard variance. So this is again a design choice. Like you might be wondering like, how do I know what this should be? You don't, like we are just modeling it. Like we understand Gaussians well. That's why people try to model this again as another Gaussian. So what, again, don't worry about all of this. This is just like a log likelihood formula for a Gaussian distribution with the mean which is predicted by mu theta, like again a neural network, and sigma is just the variance of this this distribution we are trying to model. And for simplicity's sake, we decided to keep it constant and not learn it. This can also be learned, like, but we made a choice like let's not learn it, let's keep it constant. Okay, so then the term boils down to this whole form. Don't worry about it. So like I said, right, like all of these are constants, and usually in neural network optimization, what we typically do is we kind of try to drop off all the terms which are constant and don't want to pay attention to them. So the only thing that is not constant in this whole equation is this term, like this L2 distance between x and mu theta of z. Okay, so so we want to find, so essentially like we can do the optimization, like where we are learning the weights by minimizing this objective function instead of this whole thing, like just minimize, like try to minimize the L2 distance between x and mu theta of x given z. Okay, let's try to understand what it means. Like, so it means this neural network is predicting, it takes the noise, some noise z, and it predicts a mean of a distribution, and we want our real sample x as close to this mean as possible. So that's why this term is called reconstruction term, where we are using a neural network to predict back the image given the noise. Okay, so is this good enough to train a neural network? Turns out, I mean, you can train it, but it's not good enough to produce like realistic looking images, because I mean, this is literally like one of the two terms of the GAN, and literally even GAN needed like additional law called discriminator loss to learn a good theta. So in VAE, they kind of have like another function. Like, so we kind of used a neural network to go from noise to the image, right? Like, so now in VAE paper, the authors also used another function to go from image to noise. So we have like this image, which is like a really high dimensional, complicated looking distribution, which we don't know anything about. And then we have a noise distribution, like, which is a Gaussian. So how do you go from image to this particular noise? Like, there is no closed form solution to directly go from image to noise. So that's why we kind of use another neural network to learn this. Like, so we represent this neural network as Q, which is parameterized by this phi, where we want to predict the noise given an image in the training data. Okay, and how do you learn this this phi? So since we already approximated, like this Z is going to be a Gaussian distribution, let's try to bring these two distributions closer to each other. So the first distribution is Q phi Z given X, where we're trying to learn a distribution given image. And then the second term is like a Q of Z, which is just a Gaussian distribution, like a standard normal distribution. And we want to bring these two distributions to be closer to each other. Like when you have two distributions, like, and you want to kind of compute the loss between them, you usually use like Cohere divergence. So this is that's why it's called prior matching term, because we assume the prior is going to be a Gaussian. Okay, so combining these two terms, like we have the prior matching term and we have a reconstruction term, and this is usually like the total loss you optimize VAs with. And one point I just want to mention is like, I mean, if you actually look at like the VA blogs or papers, they start with like elbow. There's something called the evidence lower bound, so which can technically be derived. Like, so log p of x is like, let's say like p of x is the distribution that is representing how images are generated, and this is just the log probability of that particular distribution, and it can be shown that this term is always greater than or equal to this right leg term. So we should strive to make this term as high as possible. That way, hopefully, we will bridge the difference between this left hand side and the right hand side as much as possible. Okay, so just keep that in mind, because we'll be coming back to it a little bit later in diffusion models. Okay, so in VAs, like kind of we are doing in single step, right? Like we are going from image to noise, and then back from noise to image. So what if we don't want to do that in a single step, but instead do in multiple steps? So yeah, this is what the hierarchical VAs do. So where on the left hand side we have an image, and then right hand side we have like a pure Gaussian distribution, or whatever our prior distribution is. So what if we use like multiple encoders to go from the image distribution to the noise. And similarly, we want to use like a lot of denoisers to go from noise distribution to the image distribution. And this can be done, and people have tried it. However, the quality is not very good yet. So and then, like, what if we kind of go from like, okay, TLDR, like we can technically go from hierarchical VA to the earlier diffusion formulations, sorry, not just earlier, like the diffusion formulation as well. So let's we have this picture, right? Like, so first thing is, let's make this hierarchy very deep. So usually hierarchical VAs are like 7 stages or 10 stages and so on. Nobody has tried like even much deeper stages. However, just make this very deep, maybe make it 1,000 steps deep, 1,000, like make this hierarchy like really deep. And the second thing is, let's have like a fixed encoder. That means like these Q distributions, which are going from the image to the noise, like this process usually like is called forward process. And let's just make it fixed. Like let's have analytical solutions for this instead of learning with a neural network. And then the next step is like, let's try to make all the decoders share the parameters. Like what if instead of learning different neural networks to perform each of these tasks, let's make all decoders share the neural net, share the parameters. However, we can give the distinction with a time embedding or I don't know, depth embedding or something like that. And lastly, like focus all learning on denoising. I mean, this is sort of a downstream to our fixed encoder point. Like if once we have the encoding part is fixed, then all our neural networks are weights are focused only on the denoising, and that's where we want to use all the back gradients to only learn the decoders. Okay, so yeah, that kind of lays like somewhat of a foundation to the diffusion models. Yeah, again, to reiterate, so it's this sort of like sort of natural progression to like the hierarchical VAs, like I mentioned, with all the differences I have mentioned in the previous slide. So again, let's try to kind of understand the terminology here again a little bit. So it's in usually most of the diffusion model papers, if you see like the image is usually represented by X naught. Just remember it, it's just the terminology. And XT, this capital T, usually means noise, like pure isotropic Gaussian noise. And then over time, in the forward process, we are adding a little bit of noise in each step. So as you can see, like in this dog example, over time, like we are adding more noise, and eventually until the whole signal in the image is completely destroyed, and the only thing we can see is pure noise. Yeah, and then and like I mentioned before, this forward process is completely analytical. We can compute it. We don't need any neural network to learn this. We just have like a formula to do it. Okay, so and then we have this reverse process or a backward process or denoising process, where we want to sample from this Gaussian distribution, and we want to remove a little bit of noise in every step until we reach a realistic looking image. Okay, so the forward process is where we are destroying the information. Reverse process is where we are kind of start from the noise and kind of end up in image space, basically. Like, okay, so one of the first papers to actually make like get this sort of formulation to work really well is Denoising Diffusion Probabilistic Models, DDPM. And in this paper, like this is how authors define the process. Okay, so like let's say like Q of XT given XT minus 1, that means like the higher noise image given a slightly lower noise image in the previous time step. This can be defined as some constant times okay, so again, this is a Gaussian distribution. This one points to the mean of the distribution, and this one points to the variance of the distribution. Again, like don't you don't have to remember any of these things. You can always refer back to them. Just try to get the intuitions. So let's take a moment to actually understand like what's happening here. So all we are trying to say is if we want to create xt given xt minus 1, first what we do is we just want to sample from this normal distribution. Okay, so what is the mean of this distribution? Mean of this distribution is my input, and which is scaled by some number. Okay, whenever you see alpha t's or alpha bar t or beta or anything or sigma, usually they're all predefined. Like you kind of set them before your experimentation. You just set them. Like you're not learning them. These are not coming from some math or anything like that. Usually, like when you are doing the generative modeling, you kind of make a bunch of approximations, and this is the approximation the authors from this particular paper made. Okay, this can be completely different thing too. It's not set in stone that this root of alpha t has to be here. Okay, so it's just the only thing to notice is it's a time dependent value. So this root alpha t, how much you are kind of scaling your input kind of depends on the time. Okay, yeah, and then if you look at the standard deviation of this distribution, again, it's also a time dependent value, but it's not dependent on your input. Like it's just a time dependent value. So this term is completely, we are not learning anything. We are just set it in the beginning, and that's all. Okay. So when you sample, so that what does that? So this is the form of how we define this distribution, right? Like so, when you want to sample from this distribution, like we have seen this formula, right? Like you kind of sample a random noise from unit normal distribution, and you just scale and shift it. That's all we did here. Okay. All right. So now let's go back to this figure. And so in this DDPM paper, the authors have analytically defined like what the forward process is going to be. So that means like we don't have to use a neural network to go from image to noise. And then what about P of xt given xt minus 1 given xt? So what does this mean? Like, how do you remove the noise? Like, how do you compute the image with little less noise given more noised image? So for this one, we don't have a closed form solution for it. Like for the forward process, we can decide what it should be like analytically. However, for the reverse process, we don't know how to do it, like because there is no closed form solution for it. So we want to learn it with a neural network. So all the P's are learned, like all the they are going to be learned using a neural network. And the next question is like, so yeah, you define a neural network like which can take xt and then can predict xt minus 1. Now, how do you train this neural network? You need an approximate distribution, and then you can just reduce like how do you do training usually? Like you have a process which you want to learn using neural network, and then you have a proxy process like which you can access during the training time, and you kind of try to reduce scale divergence between them or L2 distance between them or something like that. So TLDR, what I'm trying to say is we want to learn these three distributions with a neural network, and we need a proxy process like Q distribution, which perhaps we can access in the training time. And then what we can do is reduce the scale divergence between these two. That way we can learn the weight of this particular neural network P. Okay, so fortunately, like we can compute the posterior distribution, this Q of xt minus 1 given both xt and x naught. So again, like don't worry about like the scary looking equations. All it is saying is we can actually compute xt minus 1 less looking noise term given xt, which is a little bit more noise term compared to xt minus 1, and also x naught, like the image where this whole thing has originated from. So we can write like an analytical solution for it, where this some super complicated looking term, again, don't worry about how it came to be. All it is trying to say is you take some time dependent constant. This whole thing is a time dependent constant, and you are just scaling xt with it, and then plus another time dependent constant, and you're multiplying with x naught. So all it is trying to say is this xt minus 1, the distribution can be defined as another Gaussian with some mean and some standard deviation. Okay, and the mean is actually like lies on a line connecting xt and x naught. I mean, like I said, right, these are just time dependent constants, like and all these time dependent constants are usually greater than 1, greater than 0. So it just says like it's not necessarily have to be an interpolation, it can be extrapolation also, but this xt minus 1 lies on the line connecting between xt and x0. Okay. Sorry, I think there's a question. How do I access questions? Guys, how do I access questions?
So it's in the bottom right, meeting tools, and inside the meeting tools there is Q&A.
Right.
So it's the 9-dot menu on the bottom right.
But okay, I see it. I can see on the in-call messages. Okay, can you read out the question? Maybe perhaps.
Yeah, I can read out the question. So the question is probability of xt minus 1 given xt also a Gaussian distribution?
Yes. So good question. So we are kind of like VAs, we have also approximated p of xt minus, p of x given p theta of x given z, also as a Gaussian, right? Like where we are predicting the mean. Mean is parameterized by the neural network, and we set the variance constant. So here also we have the same approximation. All p of xt minus 1 given xt are also modeled as Gaussians. Is there a relationship between? Oh, I wish I can. Okay, let me. Okay, thank you.
Is there a relation between P and Q at any given time T?
So that is the whole thing we are trying to model. Like, if we have a distribution that is this Q of xt minus 1. So basically, like this term and p of xt minus 1 given xt, we are trying to learn, say, like bring these two distributions closer to each other. That's what we are trying to do when we are training a diffusion model. Does that make sense? Okay. Cool. All right, let's move on. So yeah, so we are able to actually compute this posterior. This one is called true posterior, where if we have access to both x naught and xt, we can compute xt minus 1. So you might ask the question, like, if we already have like a closed form solution, why are we training a neural network? So the reason for that is like simple and obvious. During inference, we don't have access to x0, right? Like, so that's why we have to approximate a neural network to get this, predict this for us. Okay. All right. Okay, there is another small simplification. So we have seen a couple of slides back, like DDPM authors have defined what Q of xt given xt minus 1, and you keep like, and then xt can be written as some scaling times xt minus 1 plus some noise. So you can keep doing, like, replace this with some equation with xt minus 2, and then again replace with xt minus 3, and so on until all the way to x naught. So we can write in a closed form, we can actually compute xt at any given point of time. Given your input image, you just scale it with another time dependent constant plus another time dependent constant scaled by like a noise sample from a Gaussian distribution. So let's take this equation and sort of substitute it here. So here we just again, like this is what authors have defined in that particular experiment. Again, like alpha t's are all time dependent terms. So when you substitute it here, we can actually get an even simpler approximation only in terms of xt. where you can compute the mean of this particular posterior distribution as xt scaled by some constant time-dependent constant term minus some another time-dependent constant term scaled by epsilon, where epsilon is the noise. Whenever you see epsilon, just assume it's a noise sample from a Gaussian, unit normal Gaussian distribution, that's all. So, okay, let's look at the variance term for a second. So let's see like if there are any variables here or dependency on xt. There's nothing like that. This is again like a time-dependent constant multiplied by another time-dependent constant divided by another time-dependent constant. All of this is just going to be a scalar which you can compute. And this is literally set at the beginning of your experiment or something like that. And this can definitely be varied and so on. Okay, finally, let's kind of try to write a similar loss function to VEs, right? Let's try to construct this equation step by step. Okay, don't like look at the equation first. Okay, so in this figure, let's look at each of these functions we have defined. So q of x1 given x0. Do we have to learn anything here? No, because we kind of decided like forward process is going to be an analytical solution. We can just compute it. We are not using a neural network to do it. So the only terms we want to learn here is the backward process, basically like all these p of x t minus 1 given xt sort of distributions. So anyway, like you can also write like an elbow sort of evidence lower bound sort of an equation for this whole process. And it kind of comes down to these three main terms, okay? Okay, let's look at the first term. So it says, what is the likelihood of x0 given x1? So essentially, it's this term. So this term should remind you of the reconstruction terms from VAE. Okay, so because x0 is a sample we have access to, it's not a distribution. So we can technically compute the log likelihood of this particular sample under this Gaussian distribution. So that's why the first one is just the reconstruction. And the next one is the prior matching term. So what it says is like we kind of ended up with this some distribution for this xt data point, right? Like, and we want this this last term, especially like the whatever the samples that are coming out of here to be as close to a true posterior Gaussian distribution as possible. So that's all we are doing. We are kind of trying to say like, okay, let's try to make this as close to Gaussian as possible. Like, yes, we kind of defined it, but let's also additionally make sure like this is as close to Gaussian as possible. And lastly, like this is actually the main loss function of this whole denoising process. So what are we trying to do? I have already sort of alluded to this before. What we are trying to do is we want to learn KL divergence between these two functions. The first function is the posterior, where we can write in a closed form where what is the, this distribution, like the q of xt minus 1 given both xt and x0, and then the second one is p of xt given minus xt minus 1 given xt, which is parameterized by a neural network. Okay, so let's just try to understand this again. So we can write some analytical solution for this particular distribution, and this distribution is parameterized by the neural network, and we just want to bring these two distributions as close to each other. So that's all this whole term is doing. Like it has sigma because we want to learn all different time steps, right? Like not just one time step. And another important thing to notice is this p theta is like parameters. We are not learning different neural networks for each of the steps. We are learning same neural network, except it takes the input to it changes at each time step. Okay, and let's kind of ignore most of these terms. Let's just try to pay attention to like a single term. We are just trying to, again, like this one we can compute in the training time. We have access to both x0 and xt, and and we are learning a neural network that can accept only xt, but still be able to predict xt minus 1. So if you remember from before, like we actually have I kind of, in the basics I mentioned, like when you have like two Gaussian distributions, and if you assume both the means of these distributions are the same, and if both the distributions are isotropic, this KL divergence boils down to just the L2 distance between the means of these two distributions. Okay, so yeah, you might be wondering like why should the variance of this distribution to be same as this distribution? It doesn't have to be, but we kind of this is in our hands, right? Like we are defining what p theta is going to be. So we are deciding like, okay, fine, I will keep the variance exactly the same as this distribution so that I will have this simple looking term to optimize. Again, it's a design choice, like it doesn't come naturally or anything like that. We are making a design choice that this particular function, we are going to use a neural network to predict mean while we keep the variance constant, I mean, time dependent constant again, and keep the variance also same as this particular distribution, which we can compute analytically. Okay, so yeah, now once we have this term, the authors are like, okay, we can further simplify this. We can say like, I mean, earlier, like we also computed what mu t minus 1 in terms of like both xt and epsilon, right? So if we kind of substitute this in this equation, we kind of end up with simple, even simpler looking term, which is like so during the forward process, you can just sample some random noise, and all your neural network is trying to do is predict how much noise was added. So yeah, like instead of predicting means, they said like, okay, you can just predict noises and you can still learn this neural network, and you can still learn like a generative model. Okay, so and if you look at the term here, this is just again a time dependent scalar. And all we are trying to do is like learn a neural network that can predict the noise given xt. Please. Oh wait, I'm able to access questions now. Nice. This was a math heavy session. What do you think about using diffusion models in text generation? I am not going to talk about the text generation, diffusion models in text generation now, because I just have only 1 hour. Yeah, I'm sorry. Like I try to keep it as low math as possible, but I guess like this is the bare minimum that's needed. Okay. Okay, the next question is like, is there any reason why Gaussian distribution is the choice of modeling? So good question. So it doesn't have to be Gaussian distribution, it can be any other distribution also. However, people chose Gaussian distributions because the manipulations are easier. Like there is like a lot of math, like we know like how to add Gaussian distributions, how to like sometimes even write like a posterior of Gaussian distribution is again a Gaussian distribution, right? Like so because of all these simplicities that come up with the Gaussian distribution, that's the main reason like why they chose it. In fact, like there are papers which show like it doesn't have to be Gaussian distribution, it can be something else also. We can still train a generative model to do exactly the same things with some of the distribution too. What is the original paper that diffusion models were based on? The first paper, they were like, there was a paper in 2015, to be honest, like it's super math heavy. But one of the first papers that actually made diffusion models famous is the DDPM paper, Denoising Diffusion Probabilistic Models. So that's why I'm trying to cover it a little bit today. Okay, let's move on. Okay, so okay, the authors of DDPM decided like we can just simply drop this term, and all we do is like we can just have only this part as like our loss term. So what we are trying to do is we are just trying to predict the noise that was like given at any given time step. We are just trying to predict back how much noise we added to go from xt minus 1 to xt. That's all we are trying to do. Like that way we can just subtract it and get the original sample back. Okay, so like not that I hope you understood even a little bit of what's happening here. So like let's just look at the training algorithm of like how diffusion models are trained. Okay, so what you do is you kind of start with an image, and then we decided like, okay, we are going to noise it in multiple steps, right? Like like in this figure, like this is 0, this is t. In DDPM paper, they said this capital T as like 1000. So we are, and each of the stage, they are calling it as a time. So we are going from time 0 to 1000. And then we will progressively noise it. Similarly, in the inference time, we want to progressively denoise it. Okay, so in the algorithm, like let's say you have an image, and then you want to learn like one time step at a time. Like, I mean, of course, you can model all time steps also, but during like this batch training, like for a given sample, we just want to sample one of the time steps. And then you just sample some random noise epsilon, which is coming from the Gaussian distribution, unit normal distribution. And the first thing we have to do is like compute xt, like which we can do it in like a analytical form, because this is just what we define, like where xt is some time dependent constant scaled, like input image scaled by a time dependent constant plus some, again, another scaling times this Gaussian noise. So this is what our xt would look like in the forward process. And all we are trying to do is in this equation we came up with it, right? Like, so we kind of sample some random noise, and then we want to take we want our neural network to take this noise sample and predict back how much noise was added to it. That's all this neural network is doing. Like, take a noised image and predict back how much noise was added from the previous step to get to this image. That's all we are trying to do. So that is the loss. Like this is just xt. I just expanded xt given x naught. That's all I did here. This is exactly the same loss, and we just backprop the gradient, and we learn theta. That's all the training is. It's a very, very simple algorithm. Okay, then let's look at the sampling. So how does the sampling work? Like, so for the sampling, we kind of have access to this some Gaussian distribution of this, usually like the same dimensionality as x naught, and we kind of begin with that. Like, first we kind of sample some random point. Okay, after that, let's say like so let's say like we are at xt, right? Like, so we have actually like seen before what the mean of the particular distribution, like this particular distribution P of xt minus 1 given xt is defined as a normal distribution with mean predicted using a neural network, plus and the variance is already predefined. Like that's all. Like because we decided we will set the variance of this distribution to be same as this distribution, right? And this one has a closed form. So this is the variance technically, like I just showed it on the side here. So P of xt given minus xt minus 1 given xt, again, to reiterate, the mean of that distribution is this one, and the variance of that distribution is this one. Okay, so we can technically compute it. Like we already have access to xt, and then using our neural network, we predict the noise, and then we just compute the mean of that particular distribution. Okay, now we have the mean and the variance. And now how do you sample from this particular distribution for a given mean mu and variance sigma square? We have already seen that before in one of the earlier slides. So you can just sample some random noise and just scale and shift using this particular mean and standard deviation. Yeah, like, and then you keep doing it again and again. So essentially all you are trying to do is like you start from here, and then you try to predict the mean of the next distribution, and then sample from the distribution, and then start like use that as the xt minus 1, and then just try to predict the next distribution, and so on until all the way you will reach the norm, like some realistic looking image. That's all you are trying to do. Okay, I just wanted to show like what this variance term would look like with respect to time. Like I said, right, like we are going from 0 to 1000. 1000 means like pure noise. So early on in the process, like we I mean, when we are in the backward process, basically, like where we are going from noise to the image, like early on, we kind of add like a lot of noise because we want to explore. Like we might be starting at some random place. We want to explore a lot of regions in the beginning before getting to the final image. But over time, this like the amount of noise we add kind of keeps going down and down. Okay, so okay, let's look at one visualization of what forward process and the reverse process potentially look like. Okay, sorry. So here I'm kind of visualizing like 4 data points, like highlighted. I hope you guys can see it. Okay, so on the left side, we have the forward process, how we are going from the distribution to the noise. So let's focus on the left side first. So if you see, like over time, this in the beginning, they're moving slowly here, but over time, the steps are getting bigger and bigger and bigger. And also, as you can see, like it's extremely stochastic, like they're just jumping all over the place. And then eventually, like they will reach some point in this normal distribution. Okay, and when we look at the reverse process, like on the right side, let's focus on the right side now. So the points can start at some place in the normal distribution, and they kind of take like large steps in the beginning, and then eventually they will reach like at whatever the target distribution, and then they are still exploring, they keep going, like they're still moving even at the end. Okay, so just to give you an intuition, like essentially like in a DDPM process, what happens is you kind of take like a lot of random steps. Like in the beginning, your steps are larger. In the later on, like your steps start becoming smaller. Once it kind of gets closer to the target distribution. Okay, I'm so sorry. That's probably a lot of math. I actually expected. Yeah, I thought I reduced it, but still, like this is the bare minimum I could do. Okay, I will probably take a pause here, and oh wow, we are at time already. Okay, this is crazy. So any questions I can answer? Could you wrap up with a high-level overview? Okay. All right. So since I'm short on time and I could only finish one section, like I guess I'll have to skip rest of them. Okay, I actually want to just finish one slide to introduce like the flow matching a bit. Okay, so I want to just say like diffusion models and flow matching are very similar processes. In fact, like there are multiple blog posts like alluding to it, or even papers too. So think of it this way, like at any, I mean, like, again, X naught is the image, and you can say like, you can always represent, there is a time dependent constant. You can say like in the noising process at any given time step t, all you are doing is you're scaling the input image by a little bit, and then you are shifting by a noise amount of, again, this is a time-dependent constant, and then epsilon again is sampled from a unit Gauss normal distribution. And you can write it like as a unified form, where you scale, you multiply like x naught with some constant, and then you sample a random noise, and then you can multiply with one constant and just add these two to each other. Okay, in diffusion processes, this is defined using some complicated looking term, but in flow matching, this gets simplified. So here, what is happening is we are just doing like 1 minus t times x naught plus t times epsilon, where t is between 0 to 1. Like in diffusion process, t is scaled between 0 and 1000, and in flow matching, it's scaled between 0 and 1. So that's the main distinction. And just to give you a sense of what flow looks like, this is what a visualization of flow is. Actually, this is better image. So as you can see, the images are the points are sort of moving in straighter lines. Instead of this random exploration that is happening in the diffusion model, in the flow mapping simplifies that objective. Like instead of exploring a lot, adding a lot of noise, just like draw a straight line between a random noise in your latent space and then image. Just travel in the straight line. That's all flow does. Like it much simplifies the whole thing. Okay, actually, like this figure has it, like on the left side, we have the flow matching path, and then on the right side, we have a Gaussian path. And as you can see, like in diffusion, like there is a lot of moving here and there. That's why we need like a lot more steps for diffusion models, because there is stochasticity even in terms of sampling. But however, in flow matching, there is no stochasticity, there is determinism. Once you start at a given noise sample, you kind of always end up with like the same image and so on. Okay, anyway, TLDR is in flow matching, we in TLDR, like in diffusion processes or flow matching or anything like that, all we are trying to do is kind of come up with a mapping between image distribution and the noise distribution. And in inference time, we sample a random noise, we kind of progressively remove a little bit of noise until we get like a realistic looking image. Yeah, okay, thank you. I'm sorry guys, I didn't check the time.
Thank you so much, Gurpreet. So our next speaker has joined us. So what I will do is I will end this call for 1 second, and then you all have to join this link again. So it's just for the attendance purposes.